Am I audible to you? Am I audible to you?
Yes, sir.
Okay, good afternoon. Good afternoon to all of you.
Good afternoon.
Today's topic is components of load torque. There is mainly two component. Number one is friction torque. Number two, that is torque required to do the useful mechanical work. This is T, F, this is work. This is actually TL. And first we see the part of friction torque, then we calculate the total components of load torque. First we draw the friction torque. This is basically torque and omega. And speed. You can say also this is omega m. And first actually is this is actually nature of this is actually nature of friction torque. If we resolve it in its component, what is the nature? This is omega m, and this is torque. Equal resolve left type. If we resolve left type, we have can see that there are three actually categories or say three part. One is called stiction, which is actually staying when the motion is or say there is no motion actually. That is static friction, or you can say it is called stiction. And which part is stiction? Can anyone tell me which one is the stiction part? This is basically friction torque nature. This is basically let me talk first. It has three parts. So any friction torque can be say there is three middle portion. One is called stiction, which is basically you can say in it, or you can say when the static friction or there is no motion between object, then the type of friction is called stiction. And another part is independent of speed, and there is another component which is basically proportional to the speed, or say you can say this is speed dependent. And when actually a motor or say load is rotating in air, then there is a windage loss, and this is actually viscous type friction, and which is proportional to the square of the speed. Am I audible to you?
Yes, sir.
We can see from that diagram any frictional torque can be resolved into three category. You can say basically three category. So if PL, you can write it as the torque, or you say torque required to do useful mechanical work plus the frictional time plus B omega m plus another term is TC. Alright, here is plus C omega square. C omega m square. Actually, if we break the load torque, there is main four part. Uh, One is due to the useful mechanical work, and other three part are due to the friction part. One is actually say uh, viscous friction, which is actually proportional to the speed, and that part is denoted by b omega. Another part friction is actually say Tc, which is called Coulomb, which is called Coulomb friction, which is actually denoted by Tc, and it is basically independent of speed. And another actually torque is present, which we actually say this is windage torque, and this is proportional to the square of the speed. In many cases, actually we uh, neglect the t plus c omega square, because the tc and c omega squares part are basically too small, so we neglect that. After neglecting, we can write TL is equal to TL plus b omega. After neglecting TC, and you can say after neglecting, which part is actually neglected? Which part actually neglected? We neglect the TC plus C omega m square. This part actually neglected. Why we neglect this? Because why we neglect this? Because with respect to TL, or you can say P omega, this TC plus C omega m square part is small in many cases. So we neglect this, and after neglecting, what we get, and from the dynamic, or say you can say from the fundamental torque equation, what we can write? What is the fundamental torque equation? It is, can you tell me what is the fundamental torque equation? It is, Preeti, can you tell me
Yes, sir.
what is the fundamental torque equation? This is the fundamental torque equation. T minus TL is equal to J ddt of omega n. This is called fundamental torque equation. So after substituting the TL, what we get? After substituting the TL from this equation, we have to substitute TL. We have to substitute TL from that equation. What we get after substituting? Can anyone tell me what is the equation at that time? What we get if we substitute the value of TL? What we get actually?
Sir, T minus TL plus B omega m equals to J d omega m by dt.
What we get? If we substitute this, T minus TL minus B omega m is equal to J d omega dt. And after simplifying this, we can get T is equal to J d dt of omega m plus TL plus B omega m. We get that.
Yes, sir.
So now the fundamental torque equation becomes T is equal to J d dt of omega m plus TL plus B omega m. Now tell me what is actually TL? What is the name of TL? Capital TL. What is the name of capital TL? The name of the capital TL is useful mechanical work. Actually, which we have to do, and B omega due to what is the name of B omega m? What is the name of B omega m? This is basically viscous friction part. Suppose we have a load system, we are driving a load by a motor. So we have to done some work. So that is actually for to do that work we need useful torque, that is TL, and due to the friction, you say though this is rotating in air, so there's some friction is there. So and when the motor is rotating on ball bearing, so there's some friction is present. Due to the type of friction, one is called viscous friction, which is actually proportional to the speed. Another friction, which is called Coulomb friction, which is independent of speed. Another speed is called windage, or due to the same windage friction, which is actually proportional to the square of the speed. In many cases, the Coulomb friction and windage torque, say windage torque friction, is neglected. So after neglecting these two terms, we get TL is equal to T capital L plus B omega m. To substituting in fundamental torque equation, we get T is equal to J ddt of omega plus T L plus B omega m. And suppose if there is a coupling, if if sometimes we are coupling used in to couple to the load with the motor, so there may be another torque is present, which is called Te, which is K theta I, which is actually proportional to the angular torsion. You can say this is proportional to actually proportional to the torsion angle of coupling. You can say this is when we use a coupling between motor and load. So with this, now you tell me
Yes, sir.
how, now tell me how many components are there of load torque, or say yes, you can say how many part are there. What are the components of load torque? What are the components of load torque? Tell me. Actually, how many parts are there? Broadly, we say there are two parts. One is for friction, one is for friction part,
Friction torque.
and another part is useful mechanical torque, or due to the useful mechanical work, which is denoted by capital TL. And if we resolve the friction torque, how many components are there? Deepak, how many components are there due to the friction? There are three parts. One is called viscous friction, which is proportional to the speed, and another called Coulomb friction, which is independent of speed. By which term we denote the viscous friction? Deepak, tell me. Deepak,
Yes, sir.
which part is viscous friction? Which part is viscous friction? This is basically our load torque. What is the name of that torque? Capital TL. What is the name of that torque?
Useful mechanical work.
Useful mechanical work. And then what is the name of B omega m? Is the name of B omega n? It is
So viscous.
viscous friction component.
Yes.
And what is the name of TC?
Coulomb.
Coulomb friction. Actually, these are the frictional torque component. And another part is there. This is for what? C omega m square. Tell me. This is due to
A
windage
small.
torque.
Very small.
This is due to windage torque. And in many cases, and in many cases,
It is very small.
very small. The
So we can neglect it.
Coulomb torque part and windage torque part are very small with respect to TL, or you can say with respect to B omega m, that is Vixen torque, viscous torque. T Actually B omega m is viscous torque, which is large with respect to TC and windage torque. So neglecting the Coulomb torque and windage torque, we write T small l is equal to T capital L plus B omega m. And we know from the fundamental torque equation, what we know? What is the fundamental torque equation? Tell me. It is, what is the fundamental torque
AF
equation? What is the
T
fundamental
minus
torque
TL
equation?
equal to J omega J J
T
dr dt omega.
T minus TL is equal to J ddt of omega m. So if we substitute, that small t small n with capital TL plus B omega n, we get the equation like T is equal to J ddt of omega n plus TL plus B omega n. After that, if we calculate from that fundamental torque equation, we have to use this equation. We have to use this equation. And if there is a coupling between, say, load and the motor, then there is a additional torque present, which is called coupling torque, and which is proportional to the angle of coupling. The coupling torque is not always present. When we use a coupling, at that time this torque will present. Now sometimes we have seen the useful torque is proportional to, say, speed, square of the speed. Sometimes we see it's proportional to proportional to speed. Sometimes it's independent of speed. And if we draw some nature, you have to tell what are the example of this type torque speed curve. This is omega m, and this is t, say, tl, and the nature if like that. Say another, if we draw this is omega m, this is tl. Another part. Now tell me, in which case we see this kind of nature with top speed? Can anyone tell me? We have to change our topic also. Suppose we have get some the nature of the speed of car. The first actually car is TL is actually proportional to omega m square nature. You can say where we actually seen this type of car. This is in case of fan type load or say centrifugal pump or say compressor, and in case of normal fan you can say this type load torque we can see where the load torque is proportional to the speed of the proportional to the square of the speed. So the examples are, you can say, this is compressor, this is centrifugal pump. In this type we get this type of load where the actually windage type, where the windage type load torque is dominating. In case of normal hour ceiling fan, the load torque is proportional to the square of the speed. And in second case, first you say that it is independent type. Then after uh, increasing the speed, then it is increasing also. That load torque is also increasing. In second case, you can see in the first part, the torque is nearly constant, and after that when the speed is increasing the torque is also increasing nature. What are the example of this type load? So suppose a low speed hoist. In case of low speed hoist you can see this type of nature. That means when the speed is very low, actually it tends to zero, say or near equal to zero, that is there is no any other type of friction is present. So at that time you can say this is basically independent of speed. After increasing the speed, then the torque is actually dependent on speed. And the third one is in case of suppose we have a we have a roller. We have to increase the speed of a roller. What we do when we actually start that, at that time the when the speed is near equal to zero, there we required some high speed, so high torque. After rolling the roller, the requirement of torque is decreased, and after that if we increase the speed of that roller, there required much torque. That means you can say in case of anything which will be at its static position, then after that we have to increase the speed. The nature of the load speed is like figure 3. And in case of 4, where we actually see in this type of car, where the power is actually constant, you can say power of this type system is constant. Where we see in this type of load torque, or say load torque speed characteristics, where you see this type of load torque and speed characteristics. In case of say traction type, say a train, when the speed is near to zero, then we require much torque, and when the speed is increasing, gradually the requirement torque is decreasing. So the figure 4 is speed torque characteristics of a train, you can say that. It is clear to use of all the figure. It is, can you understand? It is.
Yes, sir.
Have you understand that?
Sir, this topic not clearly.
We have some speed torque characteristics, in which case we can see this type of speed torque characteristics. First, the topic we have already discussed, that the components of load torque. The first topic, have you understand? The first topic, the components of load torque.
Yes, sir.
After that, I draw some speed torque characteristics, where we have to seen, or where we have seen this type of speed torque characteristics. You have to give example. In the first curve, we can see that the torque is proportional to the square of the speed. एक्चुअली इस कर्व में हम क्या देखते हैं, ये टॉर्क स्पीड के साथ प्रोपोर्शनली इंक्रीज कर रहा है. ऐसा कर्व कहाँ दिखा जाता है, कौन सा? मान लीजिए वो, हम क्या करते हैं एक्चुअली, फैन घुमाते हैं, फिर सेंट्रीफ्यूगल पंप चलाते हैं, ऐसा होता है ना नितेश?
Yes, sir.
वो जो सीलिंग फैन होता है, उसका
Yes,
कर्व
sir.
इस तरह होता है. द स्पीड टॉर्क कैरेक्टरिस्टिक्स इज of a fan type load, where the load torque is proportional to the square of the speed. Then the speed torque characteristics of low speed hoist, where when the speed is low, at that time the torque is independent of speed. After increasing the speed, the load torque is proportional to the speed of that hoist. And where we see the speed torque characteristics of like that, when actually we have drawn a speed torque characteristics in figure 3, where we actually see this type. ऐसा कहाँ दिखा जाता है ऐसा स्पीड टॉर्क कैरेक्टरिस्टिक्स? Why we actually see this type of speed torque characteristics? सपोज मान लीजिए मेरे पास एक रोलर है, रोलर को हम रोल करेंगे, पहले क्या होगा, स्टिक्शन होगा ना रितेश?
यस सर।
स्टिक्शन होगा। स्टिक्शन क्या क्या होता है? व्हाट इज स्टिक्शन?
अपोजिंग फोर्स होता है।
अपोजिंग फोर्स तो होता है, लेकिन ये कब होता है? when there is no speed between two surface. At that time the friction is called static friction or stiction. मान लीजिए आपको एक रोलर को लेके जाना है, रोल करके, तो क्या होगा? बोलिए।
यस सर।
First we have to roll that roller. So when we push the roller, at the time of starting, is there any speed?
नो सर।
At that time the stiction is more, तब क्या होगा? तब फ्रिक्शन ज्यादा होगा ना?
यस सर। एट द स्टार्टिंग टाइम
हाँ,
इज मोर
स्टार्टिंग,
फ्रिक्शन।
जब हम स्टार्टिंग कर रहे हैं तब स्टिक्शन के लिए ज़्यादा एक्चुअली टॉर्क रिक्वायर होता है। उसे जब पुशअप करते हैं, मान लीजिए अब आप अगर पुश कर रहे हैं, एक रोलर को पुश कर रहे हैं, तो ज़्यादा पहले क्या ज़्यादा फोर्स लगता है ना? उसके
यस
बाद
सर।
उसके बाद क्या होता है? आसानी हो जाता है उसे ठेलने में।
उसके बाद फ्रिक्शन डिक्रीज कर जाता है।
हाँ, उसके बाद फ्रिक्शन डिक्रीज कर जाता है, क्योंकि
हाँ।
क्योंकि क्यों वो जो स्टिक्शन का वैल्यू ज़्यादा होता है, डायनामिक फ्रिक्शन से ज़्यादा स्टिक्शन का वैल्यू होता है।
स्टार्टिंग में सर स्टैटिक फ्रिक्शन का ज्यादा रहता है डायनामिक फ्रिक्शन से।
हाँ,
फिर
स्टैटिक
आफ्टर
फ्रिक्शन
सम
ज़्यादा
टाइम
रहता
से
है।
डायनामिक फ्रिक्शन से।
हाँ, स्टैटिक फ्रिक्शन ज़्यादा रहता है डायनामिक फ्रिक्शन से।
हाँ।
तो इसीलिए देखिए, जो कार पहले जो स्टार्टिंग में जो टॉर्क है उसका वैल्यू क्या है? ज़्यादा है। स्पीड जब जीरो, तब पहले क्या
यस सर।
ज़्यादा टॉर्क लग रहा था। फिर जब थोड़ा सा स्पीड आ गया, तब क्या होगा? टॉर्क रिक्वायरमेंट घट जाएगा। एट दैट टाइम द रिक्वायरमेंट ऑफ लोड टॉर्क इज लेस। आफ्टर दैट व्हेन द स्पीड इज इंक्रीजिंग, अब इसके बाद हम स्पीड ज़्यादा बढ़ा रहे हैं, तो क्या होगा? तब एयर फ्रिक्शन आ जाएगा। एयर फ्रिक्शन आ जाएगा ना?
यस सर।
तब टॉर्क रिक्वायरमेंट स्पीड की साथ प्रोपोर्शनल होगा। ज़्यादा, जब जितना स्पीड बढ़ाएंगे उतना टॉर्क रिक्वायरमेंट बढ़ जाएगा। तो फिगर 3 एक मान लीजिए एक रोलर की स्पीड टॉर्क की कैरेक्टरिस्टिक्स है। अब 4 क्या कहाँ देखा जाता है? कैरेक्टरिस्टिक्स 4,
टेन।
ट्रेन, मान लीजिए एक ट्रेन है हमारे, जब स्पीड कम होता है तब ज़्यादा टॉर्क लगता है। इसलिए कौन
यस
सा
सर,
मोटर हम यूज
इनवर्सली।
करते हैं स्पीड ट्रेन में? Which kind of motor are used in
सीरीज।
train? Series type. Why?
या। यस सर।
Why?
इट्स हैविंग हाई स्टार्टिंग टॉर्क।
Because the series motor gives us a high starting torque.
यस सर।
Okay. Then we will move to steady state stability. Then our topic is steady state stability.
Sir, DC series motor always starting with load.
Yes, there should be
Yes
some
sir.
load at the time of starting in case of DC series motor.
ओके,
नहीं तो क्या होगा?
बर्न हो जाएगा, जल जाएगा।
बर्न हो जाएगा?
नो,
नहीं, क्या होगा? बर्न तो नहीं होगा।
बर्न नहीं होगा, लेकिन सीरीज मोटर ऑलवेज लोड कनेक्ट करके ही उसको ऑपरेट करना है।
क्यों? Why we have to start a series motor with a load? Why? Tell me. Tell me why.
फील्ड वाइंडिंग इज सीरीज विद आर्मेचर वाइंडिंग।
That's why what happened?
इसका एग्जैक्ट आंसर, ये क्वेश्चन है सर, बट इसका आंसर माइंड में नहीं है
तो उसका आंसर आप लोगों को मालूम नहीं है?
अभी सर थोड़ा सा रिवीजन करना पड़ेगा, लेकिन
अच्छा,
अभी माइंड
ठीक है।
में नहीं है ये।
पहले बोलिए, जो डीसी
हाँ,
सीरीज का
यस सर।
स्पीड का इक्वेशन क्या होता है? Speed equation. What is the speed equation of DC series motor? This is the speed equation in case of DC series motor. Have you remember that? ये पता है ना आपको?
यस सर।
इस इक्वेशन को पता है ना आपको?
यस सर।
ये कैसे आता
डायरेक्टली
है?
फॉर,
ये कैसा था वो? आपको ईजी का फॉर्मूला मालूम है? ईजी इजिकल टू पी 5 NZ/60A, ये पता है ना?
ओ इज इक्वल टू NP5 बाय डिवाइडेड बाय 60A।
हाँ,
हाँ, यस सर।
दिस इज ऑल्सो इक्वेशन ऑफ बैक EMF.
हाँ, यस
So we can write from that equation N is equal to EB by K into phi. From that equation we can write that from that equation. What is the value of K at that time? What is the value of the K at that time? P Z by 60A. You can say
सर।
the value of K is PZ by 60A, because when a machine is manufactured at that time the number of pole, number of total conductor and number of parallel path between two brushes are constant.
यस सर।
So we can write the speed equation is EB by K phi. And what is the motor equation? What is the motor equation? V is equal to EB plus IRA. This is motor equation. From that we get EB is equal to V minus IRA. So we can write the speed equation of a motor is like that. Can we write that? It is बोलिए.
यस सर।
So in case of series motor, In case of series motor, we can write V minus IARA, और एक neglect कर दीजिए फिर तो आसानी होगा समझना. V by K phi. Can we write that in case of series motor? How we do that? Because V is much greater than with respect to IARA. हम बोल सकते हैं ना.
And yes, sir.
So we can write N is proportional to V by K phi, and normally V is constant because normally the supply voltage is constant. So we can write N proportional to 1 by 5, and what is the value of phi? It is proportional to field current. In case of series motor, this is proportional to armature current because at the time of series motor, or in case of series motor, the field current and armature current are same.
Yes, sir.
So we can write in proportional to 1 by IA. अगर आप इसे प्लॉट करेंगे तो कैसे हो दिखेगा? In IA, if we plot that curve, this is like that. And what about the torque of series motor? We know that torque is proportional to phi into Ia. In case of DC series motor, torque is proportional to Ia square. So you can say Ia proportional to root over torque. So here if we replace, you can say this is root tau. And if you plot this curve also, speed torque, this curve is also like that. So from that you can say the nature of that curve is like that. So what you say, when the speed is low, at that time the generated torque is low. Am I right or wrong? It is.
Yes, sir. Speed is low.
At the time of starting,
Hmm.
the speed should be what?
At the time of starting, speed should be low.
From that curve, what we see,
High.
at low speed the torque is high.
High. Inversely proportional.
uh, at the time of when the speed is low the torque is high. So if the torque is high, then what will happen?
Speed will low.
Speed will low.
Sir, torque is inversely proportional to speed.
Hmm. Inversely proportional to the torque is inversely proportional to the speed.
Yes, sir.
Not only the inversely proportional, the square root of the inversely proportional to the square root actually of the torque. From that equation we get n is proportional to 1 by t. If we plot that, then the curve is like that. Have you understand that? ये आपको समझ में आया क्या? पहले ये बोलिए.
Sir, and is inversely proportional means 1 by t.
अब मान लीजिए लोड आप दे नहीं रहे हैं मशीन में, तो
हम्म,
तब टॉर्क रिक्वायरमेंट ज्यादा होगा कि कम होगा?
कम होगा।
कम होगा। अगर टॉर्क कम है तो स्पीड कितना है? इस कार्व से क्या निकल
तो
रहा है? इस कार्व से क्या निकल रहा है बोलिए? इस कर्व से क्या आ रहा है? इस कर्व से
और कम है तो स्पीड तो ज्यादा है।
अगर टॉर्क कम है तो स्पीड क्या है?
स्पीड ज्यादा है।
स्पीड ज्यादा है।
अच्छा,
इसीलिए सीरीज मोटर में क्या बोलते हैं हम? जब भी चलाओ थोड़ा सा लोड देके
लोड को
चलाओ।
कनेक्ट करके चलाओ।
हाँ, नहीं तो एक्चुअली क्या होता है, ये जो स्टेडी स्टेट स्टेबिलिटी है ना, इसे आप लोगों को समझ में आएगा कब एक मोटर मान लीजिए यूनिफॉर्म स्पीड में घूमता है। बोलिए, ये तो आपको मालूम है। कब एक मोटर यूनिफॉर्म स्पीड में घूमता है?
यूनिफॉर्म स्पीड में तो शंट मोटर घूमता है,
नहीं
कांस्टेंट
नहीं,
स्पीड में।
यूनिफॉर्म स्पीड में कम घूमता है। मान लीजिए कोई एक्सेलरेशन नहीं हो रहा है, डिसेलरेशन नहीं हो रहा है, मतलब जो डी डी चलिए क्या बोले, डी ओमेगा डी टी कब जीरो है? मतलब एक्सेलरेशन भी नहीं है, डिसेलरेशन भी नहीं है। when the situation is come, from the
When load is
fundamental
balanced,
from the fundamental to occupation, when we uh, put that condition d omega dt, what we get?
when
What is the fundamental to occupation? Tell me first. T minus
t, t minus tl equals to j d dt into omega.
j d dt of omega m. If we put here that d omega dt is equal to 0, then what we will get?
T equal to tl.
T is equal to TL. That means the motor torque is equal to load torque at that time. That means the motor torque and the load torque are equal at that time. ये समझ में आया ना आपको?
Yes, sir.
That means if we do not put load on the motor, then the load, sorry, the machine torque is also less. We require less motor torque also. If load torque is tends to 0, if the value of load torque is tends to 0, then the requirement of motor torque to rotate the rotor, what is tends to 0? You can say. अब अगर मान लीजिए जो कोई लोड ही नहीं दे रहा है मोटर पे, हम अगर कुछ लोड ही नहीं देंगे तो मोटर को कितना टॉर्क प्रोड्यूस करना पड़ेगा मोटर को घुमाने के लिए? बोलिए।
Zero, sir. Very zero.
टेंस टू 0।
Hmm.
और ये कार्व से हम क्या देख रहे हैं? टॉर्क जब 0 है, मान लीजिए कहाँ है, यहाँ पर है मान लीजिए, तब स्पीड कितना है?
ज्यादा है सर।
बहुत ज्यादा है।
मैक्सिमम है।
बहुत ज्यादा है। अब बहुत ज्यादा स्पीड से अगर मोटर घूमेगा तो क्या होगा? बंद करेगा कि ब्रेक होगा?
ब्रेक होगा।
Mechanical breakdown happen at that time
हाँ।
if the speed is dangerously high. That means when we do not loaded the series motor, then the speed become dangerously high. If the speed is dangerously high, then what will happen?
Motor will destroy.
Motor will motor will
Destroy.
and when mechanical breakdown is happen, The bearing are also break, and so you can say the mechanical breakdown is happen. That's why we say when we have to start a series motor, we have to put some load on that. अब आपको ये इसका आंसर पता है ना?
Yes, sir.
Okay. Now we back to our topic, steady state stability. Suppose we have machine torque and load torque is like our figure. Then which one is the operating point? Say which one is the operating point or stable point? This one. This is the steady state stability, you can say. That means at that speed the motor will rotate. And you can say this is a equilibrium point. Can we say that?
Yes, sir.
Is the A point is stable or unstable equilibrium? We have to check it. We have to check what is the equilibrium point. A is stable equilibrium or unstable equilibrium. We know that when T is equal to TL, at that time what is the value of d omega m dt? What is the value of d omega m dt?
Zero, zero.
0. That means there is no acceleration or deceleration of the motor. Is there any acceleration at that time?
No, sir. No, sir. Constant.
So we can say at that time the speed of the motor is constant. We can say that.
Yes, sir.
So after that, what is the condition? Actually, when we say that A is stable point, suppose anyhow we increase the speed of the motor load system. If it turn back to the A position, then we say that the A is stable equilibrium. If the motor or the speed is not back to A point, if the operating point is not back to A point, then we say this is unstable equilibrium point. Now Ritesh, tell me when we say the A is stable and when we say that A is unstable point.
When d dt omega equals to zero.
No, this is operating point.
Huh? Hmm.
At that when d omega dt is equal to 0, at that time t is equal to tl. So this is a equilibrium point. That means at that point the motor will rotate, or you can say at that speed the motor will rotate for a long time, and that's why we are saying that this is a stable point. Now we have to check whether this stable point is or say this is a equilibrium point. Sorry, this is called a equilibrium point. Now we have to check whether this is a stable equilibrium or unstable equilibrium. When we get the condition T is equal to TL, that is called equilibrium point. That means the motor load system will run at that speed. Now we have to check whether this equilibrium point is stable or unstable. Anyhow, if we increase the speed of that system, that means the motor load torque system, we are just increase the small of the speed. We just increase the small speed of that, or you can say with respect to that point, we just increase a delta omega m speed. Then what will happen? If the motor load system is back to the a point, then we say this is a stable equilibrium point. And if the motor load system is not back to the a point, then we say this is a unstable equilibrium point. Now you have, I think you have understand what is stable equilibrium and what is unstable equilibrium.
Repeat again.
It is, have you understand
Yes,
now?
sir. Repeat again, sir. Once.
If actually what is a operating point or say equilibrium point, that means there is no acceleration or deceleration on speed of motor load system, and at that point we say t is equal to tl. Can we say that?
Yeah, yes, sir.
Yes. That means the motor load torque will rotating with a constant speed. The motor load system will run at a constant speed at that point.
Yes, sir.
Then when the speed is a constant speed, that means the motor load the motor load is running at equilibrium. If there is no acceleration and deceleration, then we can say the motor load system will run at equilibrium, and this is the a point for this load, to say for this motor load system, and a is called equilibrium point.
Yes.
And we have to now check whether the a point is stable equilibrium or unstable equilibrium. We have to check now. And how to check? Anyhow, you have to increase the speed of that system. That means the motor load system, you have to just increase the speed. Suppose you have increased the speed delta omega m, and it will go there, and you have to check now the motor, if the motor load is back to a point. If after increasing the speed, if the motor load system is back to a point, then we can say the a is stable equilibrium point. And if the motor load system is not back to the a point, then we say this is a unstable equilibrium point. It is, have you understand up now?
Okay, 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 sir. Now it's clear.
Okay, so tell me what is stable equilibrium and what is unstable equilibrium.
When omega means speed of the torque will increases
Hmm.
and return back to the equilibrium point,
Hmm.
that is stable.
Okay.
When speed will increases and don't back to the equilibrium point means it is unstable.
Yes, you are right. Now you have to check whether it is coming or not. Suppose we have increased the speed of the system delta omega. Now, what is the speed is now? What is the speed at that time?
Omega m plus delta omega m.
At that time, the speed is omega m plus delta omega m. And suppose this speed is here, and we have just mark a dotted line, and we have to now see the what is the value of machine torque and load torque at that time. What are the values of this is load torque and this is machine torque at that time when the speed is increased to delta omega m?
Yes, sir.
Tell me which value is greater, TL or T?
TL.
TL. If the value of TL is greater than T, what will happen?
Deceleration.
The acceleration it happen. So the speed is
Decreases.
decreases. And what is the operating point at that time? So motor wheel goes this type, or you can say the speed is decreasing and it goes back to the A point. The speed of the motor load system should be decreased because at that time the load torque is greater than the motor torque. So at that time speed is decreased from here to how much? Omega m. It is.
Yes, sir.
Have you understand that?
Yes, sir.
If we increase the speed of the motor load torque system, like the diagram, what we see, the motor will returning back to the operating point A. And now suppose if we decrease the speed of the system, suppose now we decrease the speed of the system delta omega, what will happen?
Operating point below the equilibrium point.
Yes, we are now we are now at the point below the equilibrium point. At that time this is TL and this is T. Which one is greater now?
E.
T is greater than TL. Below the operating speed, the condition is T greater than TL. What will happen now? What will happen now?
Increases.
Increase or decrease the speed?
Speed will decrease.
Actually, your answer is not clear to me properly. Say again.
Sir, I am not clear, sir. Speed will decrease or increase.
What is the fundamental torque equation? T minus
Fundamental
TL is equal to J
dt
ddt of
omega.
omega m. If T greater than TL is positive or negative, from that equation, what is the value of T minus TL that time? It is positive or negative?
Po- Positive.
Positive. If sorry, T minus TL is positive, then what is the value of ddt? It's positive or negative?
Positive.
That means the speed will decreases or increases.
Increases. Increases.
That means the speed will increases. So If we decrease the speed from the operating point, what will happen after that? We can easily see that which condition is at that time t greater than TL. So due to this condition, from the fundamental torque equation, we can easily see that ddt of omega m is positive. So the speed will increases at that time,
Oh, okay, sir. He increases.
and then the motor load system is going back to which point?
Equilibrium operating point.
Equilibrium point. So now tell me, is the A point is stable equilibrium or not?
Stable equilibrium.
So we can say A is stable equilibrium. Okay. I hope you have understand it clearly.
Yes, sir.
Okay. Then we go to the next type curve. Suppose I have this is omega m and this is torque. Suppose we have a curve like that. This is T and this is TL. Say the operating point is now is B. Say this point is now operating point,
Yes, sir.
or you can say this is a equilibrium point B. We have to check now whether it is stable or not. So what we do at that time? What is
Its
the
speed will increase or decrease.
yes? So we have to first increase the speed. Suppose we are increasing the speed. At that time, the value of torque are which one? This is T actually, and this is TL at that time. Now tell me which one is greater?
T
T is greater than TL. What will happen at that time?
positive.
D omega dt will positive. So what will happen?
Its speed will increases.
Speed will increases. Is the machine or motor load torque is back to the B point or is go away? That means the speed of the system is increasing or the system is goes back to the B. Say, tell me what will happen?
Increasing.
Increasing. So is the operating point is B at that time or it will go away from B? अब बी में लौट के आएगा कि बी से भाग जाएगा बोलो?
नहीं आएगा सर.
नहीं आएगा. गुड.
सर सर कैसे सर कैसे डिसाइड कर रहे हैं कि आएगा कि नहीं आएगा?
मान लीजिए आपका क्या हुआ है अभी, मेशिंग टॉर्क ज्यादा है तो क्या होगा, स्पीड इंक्रीज करेगा ना.
यस सर.
If the system speed is increases, then suppose the speed is now here, so the system will run in which speed? This speed. Suppose the system is running at that speed. What we see at that point? The machine torque is more than the load torque. That means the speed will again increase. Suppose
Yes,
there, it becomes there. And here also the machine torque is greater than the load torque. So the speed is increase again. Then the motor system load is speed that rotate with a dangerous high speed, and the system is collapsed.
yes, sir.
अभी समझ में आया क्या हो रहा है?
Yes, sir. Yeah.
Okay. Now suppose we are decreasing speed from the equilibrium point. If we decrease the speed from equilibrium point, what will happen? You see, at that time, this is machine torque and this is load torque. So, if we decrease the speed from the operating point B, what we see at that time? Which torque is greater? Which torque is
Yes, sir.
greater?
Lot TL, TL.
So what will happen at that time? What is the sign of d omega dt at that time?
No, negative.
Negative. That means what will happen? The speed will
Decrease.
decrease. If the speed is decreases, then the motor will go back to the B point or go away from B point. After getting this condition, what we see? The motor speed will decreases. If the motor speed will decreases, the operating point is goes back to the B or go away from B.
Back, sir.
बी की तरह जाएगा कि बी से भाग जाएगा बोलिए?
नहीं जाएगा, sir.
नहीं जाएगा मतलब the operating point goes away
Unstable.
from B. So now tell me, is B is stable point or unstable point?
Unstable.
That means the B is unstable equilibrium point. अभी ये समझ में आया आपको? अभी समझ में आया दीपक, रितेश?
Yes, sir. Yes, sir.
And how to define is equilibrium point is stable or not? What we actually checking? We make a or we give a small perturbation. That means a disturbance. If we give the system a small disturbance, so that either the speed will increases or decreases. At that time, we are checking which torque is more at that time. From that condition of the torque, we get the sign of the d omega m dt or ddt of omega m. From that sign, we can easily see the motor will or motor speed will increases or decreases. From that, we can say whether the system is goes back to the operating point or go away from the operating point. From that, we can say whether the we can say the operating point or the equilibrium point stable or not. From that, we can easily say. Now you have to understand. I hope you have clear how to check the equilibrium point is stable or not. Okay, then we'll take the attendance who are present now. Ritesh,
Yes, sir.
Deepak,
Yes, sir.
Preeti,
Yes, sir.
राहुल।
Yes, sir.
राहुल, आपको समझ में आया जी कैसे चेक करते हैं स्टेबल है कि नहीं सिस्टम?
Yes, sir.
प्रीति कुमारी, हैव यू अंडरस्टैंड दैट?
Yes, sir.
ओके, ओके, सी यू इन नेक्स्ट क्लास।
Hello, sir. Excuse me. Hello.
हु इज देयर? अक्षय।
Yes, sir.
ओके। ओ
Sir,
वाह।
you have not taken
ओके
attendance.
ओके ओके, अक्षय प्रजापति। यस।
Yes, sir.
ओके, सी यू इन नेक्स्ट क्लास।
Okay, sir.
ओके।
Thank you.